The Einstein field equations govern the precise geometry of spacetime. They describe how matter curves space and how that curvature dictates the motion of matter. But there is a well-documented mathematical quirk in these equations. They do not explicitly forbid moving backward in time. Under the right conditions, the math fully permits what physicists call closed time-like curves, paths through space that loop back to their own past. Einstein himself was deeply uneasy about this feature of his own work. If general relativity allows closed loops in time, it introduces causality-breaking paradoxes that contradict classical physics. An effect could precede its own cause. Theoretical physicists do not study time machines to build them. They study these geometric anomalies to stress test the absolute limits of space-time theory. In 1949, Kurt Gödel published an exact solution to the Einstein field equations. He modeled a hypothetical universe filled with a homogeneous distribution of swirling dust particles, precisely balanced by a negative cosmological constant. Because of the intense rotation of this mass, closed time-like curves are native and ubiquitous throughout the geometry of this universe. You could travel to any point in the past simply by flying far enough in a continuous circle. Gödel's universe lacks Hubble expansion, so it does not describe the universe we live in. However, his proof established that time travel is a mathematically sound output of general relativity. To preserve the unbroken chain of cause and effect inside a geometric framework that allows these loops, the traditional model of a single straight-line history has to be abandoned. This animated diagram shows a standard light cone positioned on a flat Cartesian grid. In normal Minkowski spacetime, it stands upright. This orientation strictly limits the causal movement of any object to the future. In Gödel's metric, the vorticity, the swirling motion of the dust, drags the fabric of spacetime along with it. The world lines of particles mathematically twist around each other. As you increase your radial distance from the center of this rotation, the frame-dragging effect exponentially increases. The light cone widens and begins tipping forward into the direction of the swirl. Eventually, you reach a mathematical boundary known as the critical radius. At this exact distance, the space-like vector field becomes null. The light cone has tipped entirely onto its side. Crossing this critical boundary means the former direction of your light cone now points into the past. An object can follow a continuous path that curves directly back to the moment of its departure. Extreme frame dragging mechanically forces spatial loops to become temporal loops. Time travel ceases to be a metaphysical issue and becomes a problem of pure geometry. To study a localized time loop without requiring an entire spinning universe, physicists model traversable Morris-Thorne wormholes. These are engineered topological tunnels connecting two distinct regions of empty space. Imagine a setup where one mouth of the wormhole remains stationary, while the second mouth is accelerated to relativistic speeds and then returned to its starting position. This diagram illustrates the resulting time dilation. Because the right portal was accelerated, special relativity dictates that it ages significantly less than the stationary left portal. But the internal physics of the throat remain connected. Time links differently through a wormhole than it does in the space outside it. The two mouths maintain perfect internal synchronization. This creates a functional time loop. A particle entering the younger mouth at t equals 10 will traverse the throat and emerge from the older mouth at an external coordinate of t equals 5. It exits 5 hours before it entered. Standard local relativity, when combined with non-trivial topology, provides the exact mechanics required to construct a backward-facing causal loop. This localized loop introduces an immediate existential threat to physics. Backward time travel generates consistency paradoxes, preventing their very own origin, and ontological or bootstrap paradoxes, where an item is trapped in an endless loop with no true origin. To defend causality against these geometric loopholes, the physics community historically adopted the Novikov self-consistency principle. Novikov's mandate states that local physical laws will actively prevent any action that creates a contradiction. It restricts space-time events into strict probability states. A mathematically consistent loop is assigned a probability of 1, meaning it happens. A paradoxical loop is assigned a probability of 0. It cannot happen. The principle operates as a theoretical patch. It attempts to save the concept of a single linear history by enforcing absolute, unyielding mathematical determinism on the timeline. To rigorously test this patch, physicists Barak Shoshani and Jared Wogan developed a 3+1 dimensional Morris-Thorne topological model. This flowchart maps a specific test case, the switch paradox. An object enters a wormhole and loops backward to hit a mechanical switch. Striking that switch actively prevents the object's past self from being launched in the first place. Under the Novikov principle, this system mathematically fails. There is no self-consistent probability state for this sequence. The result is a mathematical error, leaving the timeline in an undefined, zero probability outcome. There is also the password paradox, an ontological loop where a traveler receives a password from their future self, then travels back to give that exact password to their past self. Novikov's math actually permits this loop because the events are technically self-consistent, but it violates thermodynamic entropy. Information is generated out of nothing, without a physical cause. Novikov's conjecture is structurally incomplete. The mathematics required to maintain a single timeline causality collapse under the exact paradoxes general relativity creates. If the self-consistency principle fails, physicists are forced to ask how the mathematics of general relativity can be reconciled with a causal universe. The solution is a topological expansion of space-time geometry, known as multiple histories. As the object approaches the wormhole exit, a topological bifurcation occurs. The timeline mathematically splits into two parallel manifolds. The object emerges into the new history B, striking the switch and altering events. Meanwhile, history A remains completely undisturbed. Circular contradictions are cleanly eliminated. The cause and the altered effect now exist in completely isolated, non-interacting manifolds. In the Gödel metric, light rays emitted from an event spiral outward into a circular cusp, before violently reconverging on their exact point of origin. Resolving these geometric reconvergences consumed decades of effort from the greatest minds in physics, including Stephen Hawking. Analyzing time travel is not an engineering pursuit. It is the ultimate diagnostic test for identifying the true boundaries of physical reality. If Einstein's equations hold true, they mathematically dictate that a localized loop cannot overwrite its own native past. To maintain causality, spacetime's baseline structure cannot be a static, linear thread. It must operate as a dynamically branching multiverse.